Hello and welcome back to Calculus 1. This is the part 2 on the section 4.4 for graphing functions. So we are able to utilize all of these rules from algebra and pre-calculus and calculus to compute values and graph functions by hand. You know basic functions, square root of x, you know the ln x, you know e to the x, right? But now the question is, what is the graph of ln squared x plus 3? What is the graph for sine of x squared and stuff like that, right? So we can graph all of those by hand, and we first talk about the list. Domain, that's pre-calculus. X and y intercept, that's from algebra. 3 types of asymptotes from pre-calculus and calculus. First and second derivative for first and second derivative tests. Symmetry usually we don't use, but it can be used. That's also from algebra and pre-calc. Calculate additional points, that's algebra. And then finally graph and win. And we did one example last time for this basic polynomial function just to warm up, and we found the domain for all polynomials. It's all real numbers. X and y intercepts when you set x and y equal to 0. Compute those. No vertical asymptotes or horizontal or slant for polynomials. First and second derivative tests were done, and we had enough information to draw the graph. So now we're going to work on more examples. We use the same list. So now let's pick something that it's more interesting. We can do ln x squared plus 1. So the question is, what is the graph of this? And we can actually do a very good job. This is not going to be just a loose sketch. We actually get to calculate all the points of interest and move on. All right, so we start with number 1, domain. We know that domain of ln function is just positive numbers. We know that ln, basic ln, has vertical asymptote at 0, x equals 0. So as we are looking for the domain of this function, what we know is that ln x looks like this. So this is what we know. This is what we know. And we know that x larger than 0 is the domain for the original vanilla case, right? But now we have x squared. And x squared will allow for negative numbers as well, because any number you put in the square gets squared becomes positive. And then also 0 is allowed too, because you have a positive number. So if I go and I write ln x squared plus 1, this is always positive, or 0, right? Positive or 0. And then we add 1, which means it's going to be positive or 1. So this means that now we can use any number for the domain, because square will allow us to put negative numbers in this calculation, and when you square them you get positive number, and then plus 1 will actually also kill the asymptote. So it looks like that our domain, so domain is all real numbers in this case. We can also write it as a double bar R. So that's the argument for the domain. Two, x and y intercept. So for x-intercept, we say y equal to 0. So we have ln of x squared plus 1 equal to 0. If you e both sides, you get ln and e cancel, and you just get x squared plus 1, and e to the 0 on the other side is 1. So you get x squared equal to 0, x equal to 0, you get 0, 0. Now, last class, I said that anytime when you get 0, 0, that's x-intercept and y-intercept at the same time. So we are done there. Now, that's something that we are going to use to graph, so I put a box around it to find it easy. Number 3, all kinds of asymptotes. Now, since we have domain that it's all real numbers, that means that the domain is not interrupted anywhere, therefore no vertical asymptotes. We know that ln should have a vertical asymptote, but this is ln x squared plus 1, so it's a different function, right? It's a function composition of two functions. So this x squared plus 1 business actually killed the asymptote. So I'll write, since domain is all real numbers, we have no vertical asymptote. ln x has no hasa by default. No horizontal, no slant asymptotes. Slant asymptotes actually exist only in one case, and that is when you divide polynomial by polynomial. That's the only case when you have it for the what we call rational functions. So no asymptotes of any kind in this case. Number 4, we are supposed to find first and second derivative. So function is ln x squared plus 1. The first derivative, remember, we take the function as is, and then we take its derivative up. It's f prime divided by f. F is whatever is in the argument over here. So that's our f prime, first derivative. And now for the second derivative, we can use quotient rule, you can use logarithmic differentiation, whatever makes you smile. Let's do the quotient. So copy the denominator, take the derivative of the numerator, so that's 2, and then minus, copy the numerator, 2x times the derivative of the denominator. There we go. So this becomes 2x squared plus 2 minus 4x squared divided by x squared plus 1, everything squared. So the second derivative is given as 2 minus 2x squared divided by x squared plus 1 squared. And we need this for the first and second derivative test, which we covered last time. So now number 5. First derivative test. So first derivative test tells us the intervals on which the function is increasing and decreasing, and gives us min-max for free, which is great. So to find the first derivative test, we take the first derivative, 2x over x squared plus 1 equal to 0 to find critical numbers. So this is going to be 2x equal to 0, x equals 0. Then we work out partition. We do not have any vertical asymptotes. All we have is one critical number. We only have one critical number. We pick test points in each region. We can pick -1 and +1. And then we do the test by testing these test points in the first derivative. The first derivative is 2x, so 2 times -1 over -1 squared plus 1. This is -2 over 2, which is -1, which is less than 0. So we have a decrease. We have a decrease. So since the first derivative is less than 0, we have a decrease on our function. Then we compute the first derivative at 1, which is the other test point, which will be 2 divided by 2. Now, as I said earlier, we actually don't care about what this value exactly is. We just want to know if it's positive or negative, right? So this one is positive. So now we have increase, and it goes up. And this is that great part where you see the decrease and then increase, so we know that 0 is a minimum. So 0, 0 is a min. That's a piece of information that we get to use. And then we know that the function prior to minimum is decreasing, right? And function after minimum is increasing. So we have all of that information. Part 6 is the second derivative test, where we take second derivative, 2 minus 2x squared over x squared plus 1 squared, and we set this equal to 0 to find what we called last time inflection points. Again, cross multiply, denominator dies, we get 2 minus 2x squared equal to 0, negative 2x squared equals to -2, x squared equals to 1, x equals plus minus 1. So these are our inflection points. Calculation for this is identical to the first derivative test, except now we are looking for concavity because we are using the second derivative test. So we have our number line for the entire domain. We have two partition values, -1 and 1. No vertical asymptote, so we only partition on critical numbers. Pick test points in each one of the regions, -2, 0, and 2. Those are good enough. And now do the second derivative test using these points. So second derivative computed at -2. Go find second derivative. That's 2 minus 2 -2 squared divided by -2 squared plus 1, everything squared. Now you can go and you can compute the exact value, right? Whether it's a fraction or a whole number, you can use decimal, whatever. You can, right? You can always compute this in a calculator. But again, we don't care about the exact number at the end. We only care if the number is positive or negative. So if you can argue its sign rather than computing the whole thing, then you're good to go. So what do I have in the numerator? I have 2 minus 8. -2 squared is 4, times 2 is 8, so 2 minus 8 on top, divided by 5 squared on the bottom. You see, denominator is squared, which means it's always positive. And positive number in denominator doesn't change anything, because if you divide negative by positive, you get negative. If you divide positive by positive, you get positive. So the fact that the denominator is positive, you can just ignore it. Again, we don't care about the exact value, we only care about whether it's lesser or larger than 0. So what you actually have is a negative divided by a positive, and that's equal to a negative, which is less than 0, so we have concave down. So if you can make the argument for if you can make an argument for positive or negative without calculating, that obviously speeds up your calculations, because now you have to do this at 0, then you have to do it at 2. Sometimes you have maybe 3 critical numbers and then an asymptote. When you're going to have 5 of these points, and if you are computing all of them, you're wasting a lot of time. So what we do instead is we just make a quick argument. So we have now, and I'm not even going to write, this is just squared. So I have a positive divided by a positive, which is equal to a positive, which is larger than 0. So we have concave up. And finally, positive 2 is going to be 2 minus 2 times 2 squared divided by 2 squared plus 1, everything squared. Again, I don't care about the denominator. The top is 2 minus 8, so that's negative again, divided by positive on the bottom is going to be a negative number, which is less than 0, which is again concave down. Now, these do not have to alternate. They don't have to alternate. So, you know, you can have concave up followed by concave up, concave down followed by concave down, or alternating. Depends on the function, depends on the problem. So now we have enough information. We have our concave ups and concave down, we have increase and decrease, we have our x-intercepts and minimum and no asymptotes to guide the function. So we are going to attempt the graph, and then if we need extra points, we'll just compute whatever we need. But we should be good to go to graph at this point. Since I have the entire domain, I will draw the axis in the middle like this, and then we have 0, 0, which is a minimum. If you have a minimum, you got to put a smiley face through it, right? Because in order for it to be a minimum, right, it has to be minimum on the bottom. If it's a maximum, you put a frown, because it gets a max. Now we still need to compute y values for -1 and 1, because those are your inflection points, which is where concavity changes. So we need to compute these inflection points. So we will find y for -1. Now that's original function, which is ln of -1 squared plus 1, which is actually ln 2. We'll learn later how to calculate ln 2 without a calculator, which is a really cool thing. And y of 1 is ln 1 squared plus 1, which is also ln 2. So now ln 2 is about whatever, doesn't matter, 1 point something. So we're going to go at 1 and -1 and just go. Let's see, again, we'll calculate later what the value is. No, it's actually less than 1, about 0.7 or something. Yeah, 0.7, about 0.7. So these inflection points will be here and here. So this is 1 ln 2 and -1 ln 2. All right, so I need to have a concave in the middle. You see it's concave up. Concave up is going to be a piece that holds the water. And at these concavity points, it changes outward like this because now it needs to be concave down on each of the sides. The graph is going to be symmetric. And now if you take a look at all of the features, it makes sense. You see that this part over here is decreasing to match our first derivative test. This part is increasing to match our first derivative test. You do have a minimum. And then to match the second derivative test, you have piece that it's concave up in the middle, and you have two pieces on a side that are both concave down. Now, one of the greatest things of your existence now is that you can check these nicely and easily using graphing utility. So you will go and quickly take a look, right? Use the software. We'll use Desmos here. You go use software to figure out quickly what your graph is, and there it is. As soon as you type in, this is exactly what we have. And we were able to get this by hand. So now we can zoom in, and you can see that at -1, right over here where the arrow is, -1 and about 0.7 is where the inflection point is. So that part to the left is going to be concave down, and the part to the right is going to be concave up. And then opposite here on the other side at 1 and ln2, which is arrow on the other side now. At that point, which is inflection point, you have concave up to the left and concave down to the right. So inflection points are where the concavity changes, meaning from concave up to concave down. Great. Questions, concerns? If there are none, we can take a look at something else. We have this wonderful e to the x, square roots, trig, inverse trig. What should we do?
Trig.
The one with the cosine, one with the sine, with the inverse tangent. There's the inverse tangent. Ooh, shiny. That one should be fairly quick. This is problem 35. We are supposed to graph the function y equals, or f of x equals, inverse tangent of x squared over square root of 3. So, again, graph, right? Oh, I forgot that I am on the wire. So inverse tangent x squared over root 3. How awesome is that you can graph this by hand, right? Cool factor through the roof. Enthusiasm not so much right now, but it's going to get better, right? So what do? Well, we start with the domain. What we should know is that the basic inverse tangent graphs as this squiggle like that, and it has all the real numbers, right? And this x squared divided by root 3 is not going to change that at all, because we don't have any restrictions on positive numbers, negative numbers. There are absolutely no restrictions in the basic inverse tan, so this is just inverse tan x, right? That's supposed to be our basic knowledge. So we are looking at this and we say, all right, so we don't have any issues with with the domain to begin with, and now when you start squaring x and so on, we are not adding x in the denominator anywhere to create issues with 0 or something, so domain remains all real numbers. That doesn't change in any way. So that's number one. Number two, x and y intercept. So for x-intercept, we set y equal to 0, which means tangent inverse of x squared divided by square root of 3 equals 0. We hit this with a tangent on both sides, and we have x squared over root 3 equals to tangent of 0 is 0. When you cross multiply, you get x squared equals to 0, and finally x equal to 0, which gives us 0, 0 point, which at the same time becomes x and y intercept because it's 0, 0. Number 3. Since the domain is all real numbers, implies no vertical asymptote. So that's very important. Vertical asymptote is the interruption in the domain. Since there are no interruptions in the domain, that means there are no vertical asymptotes. Great. Now, we used to have horizontal asymptotes. Again, no slant asymptotes, because this is not rational function with a polynomial divided by polynomial, so no slants. The only one that we could have would be the horizontal asymptote, right? So now, where is the horizontal asymptote? Well, the original problem had the horizontal asymptote at pi over 2. So for horizontal asymptote, if you have tangent inverse of x equals y, horizontal asymptote was at y equals negative pi over 2 and y equals pi over 2, right? Those were the two asymptotes before. Now, would anything change for this one? Well, we know the way to find these asymptotes using the limit. Set limit to infinity and see what we get. So if we use the limit of x goes to infinity and you plug in the tangent inverse of x squared over square root of 3, well, this is going to behave the same way, right? It's just going to be inverse tangent of infinity, which is the same as the one above, right? So it's going to be equal to pi over 2 again, because whether you send tangent inverse to x to infinity or you send tangent x squared to infinity or anything of those, they always behave the same at infinity, because you're only looking at the tangent of infinity. Infinity squared is still infinity, divided by root 3 is still infinity, so you still have inverse tangent of infinity. So the locations of these don't change, so we still have the same locations for our asymptotes. So you do need to know the basic case, and then you can upgrade from there. Now, our function is inverse tangent of x squared over root 3. The next is to take the derivatives. So now, we know that the derivative should be 1 over 1 plus x squared, but now we have to have fx squared and then the derivative in the numerator as a chain rule. So that would be our calculation. So I have 1 plus, and now function as is squared, which is the inner function, so that's x squared over root 3 squared, and then its derivative here, which is going to be 2x over root 3, goes in the numerator. So that's just a basic derivative. And now I fix this as much as possible. So now this is x to the 4th divided by 3, and then I multiply by 3 to get rid of the double fraction, at least in denominator. So this is 6x over root 3 divided by 3 plus x to the 4th. Then I rationalize here root 3. So f prime of x is equal to 6 root 3x divided by 3 divided by 3 plus x to the 4th. So now these cancel. We get 2 root 3x divided by 3 plus x to the 4th. So that's our first derivative. F prime is equal to 2 root 3x divided by 3 plus x to the 4th. For the second derivative, we take, we can use quotient rule again. 3 plus x to the 4 squared, 3 plus x to the 4, times derivative on top is just 2 root 3, minus 2 root 3x, times derivative of the 3 plus x to the 4 is just 4x cubed. So now we fix this one as much as possible, because remember, we got to set this equal to 0 and calculate stuff. So I have 6 root 3 plus 2 root 3x to the 4 minus 8 root 3 x to the 4 divided by the denominator. Again, denominator doesn't matter, because when we set equal to 0 it will cross multiply into a 0, so it doesn't matter. So what do I have? I have 6 root 3 minus another 6 root 3 x to the 4th divided by 3 plus x to the 4th, everything squared. And I can factor out 6 root 3, which leaves me with 1 minus x to the 4th. Now this is an important way to simplify, because now it's easy. Right, now it's easy to do this. So now I have these, and then I go and work on my first and second derivative test. So first derivative test is our first derivative, 2 root 3x divided by whatever, 3 plus x to the 4th, and we set that equal to 0 to find critical numbers. When you cross multiply, you get 2 root 3 x equals 0, from where x equals 0, so we know 0, 0, and we can now partition. We have from negative infinity to positive infinity, and we are partitioning at 0. No vertical asymptotes again, which means that we are only partitioning on critical numbers. So negative 1 and 1 test points. Pick any numbers you want. F prime computed at negative 1. So that's going to be 2 root 3 times negative 1 divided by 3 plus x to the 4th. So I hope you see this is negative over positive, which is negative, which is less than 0, and we have a decrease. Plug in positive 1, it's 2 root 3 times positive 1 divided by 3 plus x to the 4th. That's going to be positive over positive equals positive larger than 0, and now it's an increase. So we get for free that our point is a minimum. Okay. Part 6, second derivative test. We take our second derivative, which was 6 root 3 times 1 minus x to the 4th divided by something, 3 plus x to the 4th squared, and we set that equal to 0 to find inflection points. So now, when you cross multiply, the denominator dies, and then 6 root 3 also goes away when you divide both sides by it, so you just have to worry about 1 minus x to the 4 equals 0. Now that you can factor into 1 minus x squared, 1 plus x squared equals 0, and then 1 minus x, 1 plus x, 1 plus x squared equals 0. So 1 minus x equal 0, x is 1. 1 plus x equals 0, x is negative 1. And 1 plus x squared equals 0. No real solution, because the answers are complex, right? It's positive, negative I. You know that either from algebra or pre-calc, depending where you remember it. Now I have two partition points. So when I partition the domain from negative infinity to positive infinity, I have negative 1 and 1. Pick test points, negative 2, 0, and 2. Maybe you can pick better ones. Second derivative computed at negative 2. 6 root 3, 1 minus negative 2 to the 4th, divided by 3 plus negative 2 to the 4th, everything squared. Same arguments. Bottom is squared. That's always positive. On top, what do I have? This is always positive. And over here I have 1 minus a larger positive number. So this is positive minus a negative, which is larger. So I get negative for the entire parenthesis, because I have positive number minus larger negative. So that's going to be negative, and then I have a negative. So it's a negative, which is less than 0, which is concave down on the first part. Now, you can immediately write concave up here, because at 0 is a minimum. And a minimum, right, only if it's concave up, you can have a minimum. You can immediately do that. But then, again, this is math. Everything has to check out. So 6 root 3, 1 minus 0, divided by 3 plus 0, squared, which is clearly positive, divided by a positive, which is positive, which is larger than 0, which is concave up. Finally, you can use symmetry, but you can also calculate. 6 root 3, this is the same calculation as up there, except this one is a little bit easier. Oh, that's the 4th power. So this is positive, nope, sorry, lied, negative, divided by a positive, which gives us a negative, which is less than 0, which is again concave down. The conclusions of this problem worked out to be the same as the conclusions of the previous one, which is bad, but such is life. Okay, so we have at pi over 2. Pi over 2 is about 1.5, right? So I'm going to have an asymptote at pi over 2. We are going to have a minimum at 0, 0, which means it gets a smiley there. And we have to compute y value for negative 1 and 1. So that's going to be inverse tangent of negative 1 divided by root 3. If you rationalize this, the root 3, and you kick the minus in front because it's inverse tangent is the odd function, you get negative inverse tangent of root 3 over 3. Now, root 3 over 3 gives us the negative pi over 6. So pi over 6 is a third. So those 2 points should be somewhere there. Right? That's pi over 6, pi over 3, pi over 2. They all line up. So we connect these. And then we go and we follow. So last time for ln we did not have the asymptote. Now we have the asymptote. This over here is going to be 1 pi over 6 and negative 1 pi over 6. Okay, let's see. Desmos will do the arctangent of x divided by square root of 3. Oh no, it was x squared, right? Yes, it was x squared. Now you can see it's wrong because we didn't get the there we go. Oh, you can't see. I forgot the square, and then I got the same tangent in the bottom. So your pi over 2 horizontal asymptote, pi over 2 horizontal asymptote, that's about 1.5, because pi is 3.14 divided by 2 is about 1.5 and a change. It's 1.57. Right? So it's about 1.5. And you can see that the squares work out exactly like that because this is a 2. So that's 1.5 right there, which is 1.57 is where the horizontal asymptote would be. And we'll do one more case, and this will be one of the rational functions. So we did basic polynomial, we did the ln, we did the inverse trig. So let's work out on a rational function. We haven't done that. By the way, you see these problems are a little bit long, right? So it should take you about, I don't know, 30 minutes, 40 minutes when you start practicing these, each one, and then you will speed up as you do them. Now, for exams, these problems are broken into 4 separate problems. So for the exam, I don't have the full problem like this, because you see that this we don't learn anything new, right? You know all the pieces from before. So there is a separate problem for first derivative test, separate problem for second derivative test, separate problem for min and max, right? Because those are your separate sections in this chapter anyway. And then for graphing, I give you all of the specs. I give you the inflection points and the critical points and the intercepts. I give you asymptotes. I give you everything. And you are just supposed to use that information to draw the graph. Because remember, like, imagine making a mistake on the first derivative, calculating the first derivative. Everything else is, right? Yeah, my MATLAB is going to be living hell for this one, right? So don't make any mistakes. Not a good advice, right? But it's the only one we have. Okay, so problem 33, let's say. Problem 33 has what? We have x squared plus 12 divided by 2x plus 1. So this is the situation where you have what we call rational function when you divide polynomial by another polynomial. All right, domain. Number one, domain. For domain, we take the denominator and set it equal to 0 to calculate the points that we get to kick out of the domain, because your denominator is not allowed to be 0. So x is not allowed to be a half, which means the domain is going to be negative infinity to 1/2, union knockoffing 1/2 to positive infinity. So we have the domain and we have the interruption in the domain. Number 2, x and y intercept. For x-intercept, we set y equal to 0, so x squared plus 12 divided by 2x minus 1 equal to 0. Cross multiply, we have x squared plus 12 equal to 0, and that has no real solution. No real solution because you have x squared equals negative 12, and then you take the root of that, will give you i's. But then for the y-intercept, you set x equal to 0, and that's going to be 0 plus 12 divided by 0 minus 1, which is negative 12. So we do have 0, negative 12 y-intercept. And that's the point that we are going to box, because we are going to plot that point and draw the graph through it. Number 3, vertical asymptote. Well, yeah, right? We have the domain interrupted at the 1/2, which means that's where it's not allowed, right? So we have x equals 1/2 vertical asymptote. Horizontal asymptote. We only have horizontal asymptotes if the exponents are the same or the denominator has larger exponent. So we don't have any, right? So in this case, the numerator has the higher exponent. So x to the p over x to the q, p larger than q. No. Ha. So this is something that you have from your pre-calc, or you can go take the limit and you will see. Slant asymptote. Yes. Because p equals q plus 1. So if the degree in the numerator is by 1 larger than the degree in denominator, we learned in pre-calc 1 that there is the slant asymptote, and we have to do the long division of polynomials to find where that asymptote is. So we have to divide 2x plus 1 into x squared plus 0x plus 12. I added 0x as a placeholder so we can do the division in piece. So now, x squared divided by 2x is 1/2 x. Okay, 1/2 x. Multiply back, we get x squared plus 1/2 x. When you subtract, you get negative 1/2 x plus 12. Well, negative 1/2 x divided by 2x is negative 1/4. So minus 1/4. And we don't have to calculate remainder or anything because we already have y equals mx plus b, so it's 1/2 x minus 1/4. And we box that because that is another piece of information that we will use to draw the graph. So far we have domain, we have the y-intercept, we have vertical asymptote, and now we have slant asymptote as well. Next order of business is to find those derivatives. Now I'll show you a very easy way to find it. So we have a function f of x is equal to x squared plus 12 divided by 2x plus 1. Right, this is our function. You can use quotient rule, you can use logarithmic differentiation to find the derivative. Now let's see. To find the derivative, you box this using the special key. You push math button, you go on a pull down menu and you say differentiate. Right, that's the fastest way to do the derivative. So it gives you that the first derivative is equal to 2x minus 3 x plus 4 divided by 2x plus 1 squared. All right, so that's the fastest way to do this. Then you, I don't know, yeah, just select with the special button right here on the side of your pen. There is a button right where the index finger goes, and you use that button to select. It doesn't work on that thing. Now you select this, right? You push the math button and then you click this, you say differentiate, and it gives you the second derivative. So f double prime of x is equal to 98 over 2x plus 1 cubed. Again, you can use the quotient rule, you can use the logarithmic differentiation. It's just that this is a little bit easier. So now you have your first and your second derivative, and now you can go and do the first derivative test. FDT. So we take our 2x minus 3x plus 4 divided by 2x plus 1 squared, and we set that equal to 0. From where 2 equals 0, x minus 3 equal to 0 gives us x is 3, and x plus 4 equal to 0 gives us x is negative 4. The denominator, once you cross multiply, just dies. So now, what do I have? Well, I have a lot of partitions now. I am on the infinite domain, from negative infinity to positive infinity. What do I have? Partition at negative 4, partition at 1/2, partition at 3. So these are my critical numbers. So I have critical number, vertical asymptote, critical number. So we have to partition at all of these. We have to partition at all of these. Pick a test point in each region. So negative 5, 0, 1, and 4. So we pick a test point in each region, and then we go and calculate the first derivative at each one of these each one of these test points. So I have 2 times, and then it is negative 5 minus 3, negative 5 plus 4, divided by something squared, we don't care, right? We have a positive for 2, we have a negative for the next one, and a negative for the next one, divided by always positive, and all together it's a positive. So we have the increase for negative 5. Then we use f prime of 0. 2 times 0 minus 3, 0 plus 4, divided by something squared. Positive for the 2, negative for the parenthesis, positive for the next one, divided by a positive, all together is a negative, less than 0, decrease. Now we calculate at 1. F prime at 1 is 2, 1 minus 3, 1 plus 4, divided by whatever squared. As soon as it's squared, it's always positive, so denominator positive. 2 is positive on top, 1 minus 3 is negative, 1 plus 4 is positive. We are getting negative again, meaning another decrease. And finally, we are computing this at number 4. F prime of 1 is going to be 2 times 4 minus 3, 4 plus 4, divided by something squared. And this is going to be positive across the board. All of the factors are positive, larger than 0. So we have increase. What do we get for free? We get for free that the negative 4 is a max, and at 3 we have a min. Graph shows that. You see that it looks like this above negative 4. Well, that has a max. And you see that it looks like this, right? Decrease and then increase for 3, which means 3 is a min. Now we need the y values for these, so we can find quickly the y value for f of 3. Plug 3 in original problem. That's going to be 3 squared plus 12 divided by 2 times 3 plus 1. 9 plus 12 divided by 7. So that's 21 divided by 7 is 3. So minimum at 3. And y for negative 4 is negative 4 squared plus 12 divided by 2 times negative 4 plus 1. Negative 16 plus 12 divided by negative 4 times 2 is negative 8 plus 1 is negative 7. So this is 28 divided by negative 7, which is negative 4. Well, how convenient. We have 3 point, which is a min. And we have negative 4 as a point, which is a max. So these are pieces of information we're going to use to graph. Great. Second derivative test. We take our second derivative. So that was 98 2x plus 1 cubed. And set equal to 0, we get 98 does not equal to 0, so no inflection points. We still do partitioning and everything. We do have a vertical asymptote at 1/2, so we can choose a test point of 0 and a test point of 1. If you have no inflection points, if you have no asymptotes, then the entire line is one partition. So you just pick one test point somewhere. Usually x equals 0 is the easiest. So if you have no asymptotes and you have no numbers to partition with, then the entire domain becomes one partition. In this case, we had no inflection points to partition with, but we did have a vertical asymptote, so it's just 1/2, and then you pick these. So now what do I have? Second derivative computed at 0. That's 98 divided by 0 plus 1 cubed. That's positive divided by a positive, which is a positive, which is larger than 0, which is concave up. Second derivative computed at 1 is going to be 98. 1 plus 1 cubed, which is again positive, divided by a positive is equal to a positive, which is larger than 1, which is concave up. Let's graph. How is it concave up? I don't like it. You can't have min and max both be concave up. Something is terribly wrong. So 3 is minimum. Something is terribly wrong here, and here is why. When you draw the graph, it's not going to add up. So we have our half asymptote. We know that's a thing. 1, 2, 3. We can do different scale. 1, 2, 3. So here is a 3, 3. Oh, this graph is going to be really bad. Okay, let's remember that we have a negative 12, I think. Is it a negative 12? Yep, negative 12 on the y-intercept 5 pages ago. So, there we go. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 12 y-intercept. We also have half vertical asymptote. We have negative 4, negative 4, 1, 2, 3, 4, to be a max. We have the slant asymptote, which we need to graph. If you remember, that one was negative 1/4. And then we go 1 unit up, 2 units over. So now that's another asymptote. And we see that this part of the function is easy to draw because I need to go, I use red. I need to follow the asymptote. I have to go to this point, then I have to bend through max and follow the other asymptote. So this one was easy. That's our max point, negative 4, negative 4. And this piece is supposed to be concave down, but I got concave up. Why did I get concave up? What's wrong?
Maybe it's not pointing to the derivative, right?
I copied the problem wrong. That's a plus. That's a plus. So it's a negative on these. That's what's the issue. So when that's a negative, then the derivative changes, because that's a negative. So now, when I do the derivative, it changes this to a negative, and then I do another derivative, holy nightmare, is 247 minus 4x. There we go. Much better. First derivative test stays the same. Did I change my asymptote? My asymptote did not change. Good. So first derivative stays the same, which is good. It's the second derivative test that changes, because now this is what was it? 2 times 47 something? Minus 4x? 47 minus 4x or something like that? 47 minus 4x, yes. 47 minus 4x. So we are going to have when you set equal to 0 now, 47 minus 4x is I don't like this. Something did not work out here. I think that the software didn't do the derivative right. So this is what? When you FOIL, you have x squared plus x minus 12, and when you double it, it becomes 2x squared plus 2x minus 24 divided by 2x minus 1 squared. All right, let's see. If the derivative is going to work better now, or we're going to get the same. L, what? All right, got it. Now let's see. Same. This is when you quit.
So many places making this.
Maybe
crazy.
the first derivative isn't right.
The first derivative was easy, and it gave us good numbers.
Oh, it's minus 4 plus 3.
Minus 4 plus 3. Minus 4 plus 3, okay. Okay. So -4 plus 3. That's going to give us a -3. This changes now everything. I'm just going to jump real quick. Be right back. Because now everything well, okay, it's not that bad. We just need to change everything. It's not terrible, okay? We just need to change everything and the rest is good. Just because I wrote minus as a plus in the first derivative. You saw that, right? So 15 minutes of life gone, never to be recovered again. So this part of the problem is bad, okay? So we're just gonna get rid of this. So don't worry about that, right? That's not a big deal. That's that. And then we just need to get rid of this. So just this and this. We need to get rid of the 0 over here. Some of these lines, the function that we drew. So we just need to get rid of these things. There we go. And then this part here, and that point, and that's it. We don't do anything else. Just erase those, okay? And now we do partition for like nothing ever happened. From -infinity to +infinity at -3, at 1/2, and at 4. So that's -4, 0, 1, and 5. So the first derivative calculated at -4, we are going to have 2, -4 plus 3, -4 minus 4, divided by something squared. That's a positive, times a negative, times a negative, divided by a positive, all together is a positive, and it's larger than 0, so we have an increase. Great. Then we go to the next one, f prime at 0. It's gonna be a 2, 0 plus 3, 0 minus 4, divided by something squared, which is always positive. We have a positive times another positive times a negative, which is going to be negative divided by a positive. That's less than 0. We have a decrease, and at -3 we have a max. Next one is at 1, f prime at 1, 2, 1 plus 3, 1 minus 4, divided by the square. It's a positive, times another positive, times a negative, divided by a positive. It's all negative, so we have a decrease. And finally, f prime computed at 5. It's 2, 5 plus 3, 5 minus 4, divided by something squared. Positive, 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 larger than 0, and positive, which gives you a minimum here. So now those y values that we need for min and max, f of -3 is our 9 plus 12 divided by -3, that's a 6 plus 1, -6 plus 1, right? We are using -3, so it's -6 plus 1. So this is 21 over -5. So we have -3 and -21 over 5. Great. And now f of 4, that's going to be 16 plus 12. And then 4 squared, that's 8, plus 1 is 9. So 28 over 9 is 428 over 9. And those are our min and max values. So max and the min. This is getting worse by the second. Excellent. So hopefully now, second derivative test fits. We still have 98 over 2x minus 1 cubed equal to 0. 98 is not equal to 0, so no inflection points. But we do have asymptote at a half to partition from negative infinity to positive infinity. We partition with the 0 and 1. And when I plug in 0, I get negative. When I plug in 1, I get positive. Great. Woohoo! Second derivative at 0 is 98 divided by 0 minus 1 cubed. Cube preserves the sign. So this is going to be a positive divided by a negative, which is a negative, which is less than 0, which is concave down. So concave down, so -3 better be max. Yes, finally. Second derivative computed at 1. That's 98 over 2 minus 1 cubed. Positive divided by a positive equals a positive, equal larger than 0. Concave up. See, never give up. Even if you have to redo the 30-minute calculation for something that technology can get in less than a second, right? Right. So what do? We go this way, go that way. We need -12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, -12. We have the half vertical asymptote. We have a -quarter, go up, go over. For this. So now I have my asymptote, the slant asymptote. So now what I'm going to do, so I have my slant asymptote. Now I need my numbers, -3 and negative something. What was it? -3, -21 over 5. That's like -4. So -3, -4. 1, 2, -3. 1, 2, 3, 4. So somewhere over here. And then the other part was 4 and 28 over 9. That's like 27. So that's like 4, 3 almost. 1, 2, 3, 4, 1, 2, 3, somewhere over here. So for this part, we follow, go through this one and follow. Over here we follow, go through this one, go through this one and follow. It's terrible, but he has to follow the asymptote. Woohoo! Let's see. Are you afraid to check? Good. X squared plus 12 divided by 2x plus 1. I said 2x, not 21. Get used to that graph. Used to it? There it is. Same thing. Very easy, no problem, right? Good. Time for a break. Bye.